Good morning, physics. So we are going to do a tutorial right now that involves two kinds of potential energy in the same problem. Gravitational potential energy and elastic potential energy stored in a spring. Okay, so this is one of the problems that was assigned for homework. Let me show you what we're dealing with here. Here it is. So we're dealing with a situation where there's a spring that is launching a projectile vertically, and the picture here shows three different moments in time. The first moment is when the spring is completely compressed and ready to launch. It's compressed an unknown distance. The second moment is when the spring is completely decompressed, and the projectile, the moment the projectile leaves the spring launcher and starts flying vertically into the air. And the third moment is when the projectile is at its highest point. And we're given some parameters of the system here. The spring constant, 0.08 newtons per centimeter. We'll want to convert that to newtons per meter, so we have SI units. The projectile's mass, we'll want to convert that to kilograms. And the vertical height that the projectile achieves, the maximum height it achieves, above the extended spring. So above the point where it launches from, not the point where it's compressed to. Okay, and the goal is to find D, the distance the spring was compressed. And you see I found an answer here. It's about 0.6 meters. Let's take a look at how I find that answer. All right. So in this problem we have two kinds of potential energy. We have spring energy, or elastic potential energy, and gravitational potential energy. And the way to think about this problem is in terms of these three moments in time. You got the moment where you have the moment where the projectile is ready to launch. You have, we'll call that 1. You have the moment where the projectile, the spring has stretched and the projectile is launching vertically. We'll call that moment 2. And then we have the moment when it reaches its maximum height up here. We'll call that moment 3. So the things we know in this problem are this distance is 5 meters, and we also know that the spring constant is 0.08 newtons per centimeter. So if you convert that to newtons per meter, multiply by 100, you get 8 newtons per meter. And we also know the mass of the projectile is 26 grams, which is 0.026 kilograms. Okay, if we think about the work energy theorem, we have change in kinetic plus change in potential equals work done by non-conservative forces. And in order to study this problem, what we're going to assume is that there's no non-conservative forces acting on the system. There's no friction. So this ball flies vertically, and air drag and friction don't affect its motion. And if we do that, this term is 0, and what we have is the change in kinetic plus the change in potential, which can be thought of as the change in mechanical energy, E, is equal to 0. And another way to think about that is if delta E is equal to 0, the mechanical energy the system has at moment 1 will be equal to the mechanical energy the system has at moment 2, and those are both equal to the mechanical energy the system has at moment 3. So when you have conservation of mechanical energy, when you have this condition, you can set up problems by quantifying the mechanical energy the system has at any moment and setting it equal to the mechanical energy the system has at any other moment. Okay, so let's do that. And before we start though, the thing that we want to find is the distance the projectile is compressed. So you can think about this as, well, what is that distance? Well, it's whatever the y position of the projectile is in moment 1 compared to the y position at moment 2. And then, of course, the y position at moment 3 is something we can determine if we know that it rises 5 meters. So one thing you want to do here is you get to define where your y equals 0 point is going to be. And you could say my y equals 0 is the position where the spring is compressed, ready to launch. Or my y equals 0 point is the position where the projectile is the instant it leaves the spring launcher. Or my y equals 0 point is the maximum height that the projectile attains. You can do any of these. And what I'm going to do is I'm going to call this middle point, the y position at moment 2, when the projectile leaves the launcher, as y equals 0. And the reason I'm going to do this because I know from experience that this will simplify the algebraic, the look of the algebraic expression. You could get the same answer either way, but this approach will be the result in the most simple looking algebraic equation. Okay, so what I'm saying is I'm going to say that y2 is equal to 0. Okay, and at this point, make things a little smaller, I could say, well, E1, what's the energy at moment 1? Well, we have potentially two kinds of energy, kinetic and potential. So the mechanical energy at point 1 is the kinetic energy at point 1 plus the potential energy at point 1. Well, at point 1, the projectile isn't moving yet, so it doesn't have kinetic energy. What about potential energy? Well, in this case, the potential energy could be gravitational potential energy at point 1 or elastic potential energy. I'll call that S for spring at point 1. And it turns out that because I said y2 is 0, y1 is negative, so that means it has both these types of energy at point 1. The gravitational potential energy is going to be negative because it's below the point y2 that I call equal to 0. And gravitational potential energy is equal to weight, m times g, times vertical height, which is going to be y1. And it's negative because, again, you're below the point that I said is equal to 0, y2. Now the spring energy is going to be positive because the spring is compressed a distance equal to y1. Its 0 point is y2, so it's compressed the distance equal to y1. And the potential energy that's stored in the spring is 1/2 k y1 squared. Now here's something interesting. If k were really, really, really big, well, if it was sufficiently big, sufficiently large, then of these two terms, this term would be a lot larger, and we could probably ignore the gravitational potential energy at point 1 because it would be so small. And that would simplify the problem because we wouldn't have a y term and a y squared term in the equation. But we're not going to do that here because it's not really that large. 8 isn't really that large compared to the distances in this problem. So at moment 2, you can have potential, or kinetic and potential, and at moment 2, the potential energy is 0 because gravitationally you're at the point you called y equals 0, so you have no gravitational potential energy, and the spring is completely stretched, so there's no spring energy in the system. So all the energy is kinetic, and it would be equal to 1/2 m, the speed at that moment squared. And one more. At moment 3, you may have kinetic and potential. And again, at that moment, when you reach the maximum height, your speed is momentarily 0, so there's no kinetic energy. And all of your potential energy is gravitational potential energy, because again, the spring is completely stretched. so there's no energy stored in the spring, and the gravitational potential energy would be mgy3. Okay, so if we think about the things that we know here, we know the mass, and we actually know what y3 is because it's relative to our 0 point. So we know that y3 is equal to 5 meters. Okay, so we know that. We don't know v2, we don't know the speed at moment 2. What are we trying to find? y1. y1 is the amount of compression that the spring has the moment before it's launched, before the projectile is launched. So we can set any of these two energy equations, these expressions for the total mechanical energy, equal to any of the other expressions for total mechanical energy. But what makes the most sense in this case is equating E1 with E3. Okay? Because that way there'll be one unknown, and it's the thing that we're looking for, y1. So if we do that, let's go down here, we will have negative mg y1 plus 1/2 spring constant y1 squared equals mg y3. And let's write this as the standard form, in the standard form for a quadratic equation. We have two terms in here with the unknown y1 in them. 1 squared and 1 is to the first power. So we have a quadratic equation here. So let's write the squared term first. Then the term with y to the first power. And we'll subtract the constant. We could figure out what this term is because we know everything in it from both sides, and that equals 0. So we have an equation here that's of the form a y1 squared plus b y1 plus c equals 0, where a is equal to 1/2 k, b is equal to minus mg, and c is equal to minus mg y3. So these are constants, a, b, and c, that you can calculate from what's given, and then we can solve for unknown y1 by using the quadratic formula. y1 is going to equal negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. There'll be two answers here, and I solve for them. y1 equals 0.597 meters, or negative 0.533 meters. And of course, in the context of this problem, the negative number doesn't make any physical sense. We already took into account that the compression is in the negative direction when we wrote out that the potential energy at moment 1 is negative. So the answer that makes sense here is the positive result that you get from applying the quadratic formula, which is the answer that I got. Okay, so one thing to consider here before we end this tutorial is the approach that I'm taking here is using the work energy theorem in a situation where there's no non-conservative forces that do any significant work. So we can ignore non-conservative forces, which means that mechanical energy is conserved. What does that mean mathematically? The change in potential plus the change in kinetic is equal to 0. The change in mechanical energy, E, is equal to 0, which means if you could write out an expression for the total mechanical energy at moment 1, or moment 2, or moment 3, you can set any of those expressions equal to any other one of those expressions. And that allows you to write down algebraic equations that then you can use to solve for unknowns. Okay, so you have another homework problem that involves a roller coaster. Here it is. Note that the work done by the rolling friction is 0. So, the approach that you are to take here is the same approach, where you have mechanical energy at this point, this point, this point, this point. You can write out an expression for the mechanical energy at any of these points and set it equal to the mechanical energy at any of the other points, and then do the algebra to solve for whatever unknown you're asked for. Okay, but the approach, the approach of using physics tools to solve that roller coaster problem is very similar. There won't be any spring energy in that problem. There's no springs. There's just gravitational potential energy and kinetic energy to consider. Okay, hope this helps. I'll see you guys later, and